Okay, so what I've got here is I've went ahead and built the circuit here um, for the op amp. Now what I'm going to do here is kind of show you specifically where the op amp is here. So I'm going to draw a box. And then let me I thought there's a way to there we go, edit properties. So we'll make it a little bit thicker, dot it, and we'll make it green. Okay, so what's inside this green dotted box here? This is the op amp that we designed. And you can see here I'm just using two N3906s and two N3904 transistors. Now, even though you could think, oh, I could build this, no, you can't. This is, of course, all the components being matched and all sorts of great things here. So what I've done here, though, is I've set this up in an standard inverting configuration. Now notice I haven't put in my current mirrors here. I'm just using current sources. In your designs, you will need to have these not be current sources. They'll actually have to be transistors to do it, but 40 microamps and 200 microamps. So if I look at this here, I've got a 1K ohm resistor going into the negative terminal, a 5K on the feedback resistor, 1 volt amplitude signal, frequency of 1K. So the gain should be -5. Very easy for us to figure out. Right? So if I hit simulation on this and then go to my window, we can see that, yeah, I've got here, I don't know why it scaled it like this, but the green is my input signal, and that's definitely 1 volt, and then the red is the output, which is the -5 to 5. So now one thing we can do here, because we know that, I've got 10 volt power supplies, for instance, here. So in theory, the saturation voltage should be 10, but we know in reality that's not going to be the case. So let's go ahead and set the gain up to 12, just to see what happens here. So I'm going to run the simulation again with my gain up to 12, and we can see, yeah, it absolutely saturates, and it looks like it saturates right up at 10 volts, but then we definitely have some negative here that we're not saturating at. So of course we can figure out here, let me see, do I have, yeah, I have it labeled. We can evaluate a measurement. Let's turn current. We could do the max of the output voltage, and it's probably hard to see here, but it's 9.946 or 9.9, I'm sorry, 9.95 volts, so we don't get quite up to the 10 volts, but we actually got there pretty closely. Now again, this is of course simulation, but then if we look at evaluate measurement, and I know that you probably can't see these numbers just because of resolution and everything. Cancel. Evaluate measurement. Min V out. And as we get -9.28. And of course, that has to do with the fact that there is transistor biasing going on here. For instance, if I turn the voltages on here, we can see that there is absolutely going to be voltage dropping across these transistors and everything, DC voltage just to power these things up. And that DC voltage that's being used to power these transistors up takes away from what we can get as far as how close we can get to the rails. And we can also turn on the currents, for instance, and we can see you got 40 microamps going down here, 200 microamps, and you can see all the different currents going through here. So now some other things we can do as far as the simulation goes is we can say, okay, well, let's not do this in this form here like this. Let's instead I'm going to put in a DC source. There we go. So instead I'm putting a DC source in here. I'm still going to be looking at my output voltage here. It's not letting me look at that. Oh, it's probably because there we go. So I'm going to be looking at the output voltage, but I'm going to change my sweep here. Instead of doing a time domain, and of course I had to set my time domain up first off because my signal is 1 kilohertz, so I had to set that up so that I could actually get the signal correctly. But I'm going to do a DC sweep, and let's go ahead and start, instead of starting at that, I'm going to do -1 volt to 1 volt, and we'll do 0.01 volt steps. And then we're going to run this simulation. And we can see here that this right here is the linear region. So it looks like we have this very narrow linear region. And it is going to be narrow because remember, even when we talked about these back in circuits 1, you could put very small voltages in on the terminals because the gains were so large. Now, the one thing that's not as great about this particular design is our linear region isn't centered around 0 volts, which is what we'd like, but that's where you have something that's called, if you ever remember, they're talking about these, like a 741 instance has this offset null and other things of that nature where, we can shift where that load line is just by applying additional DC voltages to the circuit in appropriate places. Now the pins aren't set up to do that currently, but we're not going to worry about that too much. In fact, okay, it's a little bit off. But let's try and figure what this is. So to figure this in, we're going to have to zoom in quite a bit. So let me cancel some of these windows here. So I need to go back and edit my simulation profile. And then let's just go ahead and do -0.1 millivolt to 0.3 or 0.2 millivolt, and the step sizes of 0.001 millivolt. And yeah, I could have converted those to microvolts, but whatever. And I'm not in the correct range here. What's going on here? So I need to set up my simulation profile again. I'm basically not in the range to capture that linear region. So let's instead do -1 millivolt to 2 millivolt. Okay, there we go. Yeah, and we can see it's definitely off-centered here. So let's look at from 1 to 2 millivolts. Okay, so we can see here that we have this here. Now there's ways that we could compute this more precisely, but what I'm going to do is I'm just going to turn my cursors on, and I know this resolution is way too small for you to be able to see it. So I've put two cursors there, and I have, if I do the computation here, let me pull up a calculator, make it a little bit smaller. My V out difference is 11.89, and then my V in difference is 23.574 exponent 6 negative, which gets me a large signal voltage gain of 504,000. Which, remember, these voltage gains were in the hundreds of thousands. So we can get what that AD is, that large signal voltage gain. Now that doesn't give me common mode rejection ratio or anything like that, and it's not the differential voltage gain in the common mode rejection. This is large signal. Remember, we had two different cases. Small signal would be looking at the differential gain if I put a small signal in there. And we can look at that too in a second if we'd like to here. And maybe we will here in a second. But I could also then convert this to decibels, because sometimes it's reported in decibels that in some data sheets you'll see the large signal voltage gain reported in decibels, and in this case it would be 114 decibels. So where am I at in this video? So it's only been about 12 minutes here. So let's go ahead and see if we can look at something like the small signal differential voltage gain. So I'm going to go ahead and put in my V sign back in. Put that back in. And then I'm going to have to put in the values here. Still do 1 kilohertz. AC of 0. But then the amplitude here, I've got to think about this. If I think about here, going back here, I wasn't able to put in a very large voltage here as far as a difference voltage, like 1.4 millivolts. So let's just try it with 1.4 millivolts and see what happens here. And then we, of course, have to, we have to change my simulation profile, because now I'm doing a time domain, and I can just leave it set as that. And then we'll do, and you see we're getting a weird signal here now in the output, because, well, what I've done essentially, we've essentially saturated it here. And we're saturating it at the positive rail. So let's even go for something even smaller here. Let's try 0.1 millivolt. Yeah. So I'm just going to see if we can get this. Yeah, now what's gone down is I've gotten the signal too small as far as the amplitude, that it's not really able to simulate this. So we can't really simulate what the small signal differential voltage gain could be. Now, there are ways that you could try to simulate what the common mode rejection ratio is, because there are circuits you can build that would allow you to physically test the common mode rejection ratio. but we don't really, it doesn't really work very well in simulation. So the main thing I'm going to be looking for is you calculating what large signal differential voltage gain is, and then the other thing you can check here, and we'll look at it in the next page here, and I'll show you what it is what the gain bandwidth product would be. So what I have here now, let me show you this one here. This is a different circuit. And so let me, so it's the exact same amplifier, but now what I've done is I've added in those current mirrors. So we're going to look at seeing if we can figure out what the gain bandwidth product is. And so we can see again that I'm getting the output I would expect, and I can again increase this to, you know, like, let's just say even 8K so I don't saturate. And of course I get my gain working out correctly still. So it's the exact same design, except I've changed what the currents are. Now I'm going to turn the currents on here in a second, and you're going to notice that I'm not able to get exactly what I was designing for here. In fact, I've got 42 microamps coming down here, and actually I thought I had 200 microamps, but I actually have an error in my design, and it's got 2 milliamps coming down here. I bet if I just changed that to 60, I'd be okay. Let's see what happens. Yeah, now I'm down in the microamp range, but it's still, circuit works still the same. Okay, so let's turn those currents back off. What we want to do is figure out maybe what the gain bandwidth product would be. Well, what we're going to do actually is we're going to set the gain for 1. Now this isn't going to be an exact way to measure it, but it's going to be a roughly, okay, so we can see we get simply that they're just out of phase, right? Now you could also set this up to get unity gain if you wanted to use the positive terminals instead, so that you could get them exactly lining up. But here they're just a little bit out of phase, 180 degrees out of phase. 180? Yeah, 90 degrees out of phase. No, 180 degrees out of phase. Well, what I'm going to do here is I'm going to increase the frequency. Now, if I increase the frequency, I'm going to have to change my simulation profile. And of course, I'm not patient, so I've opened it twice. But if I've increased the frequency by 10, I should just decrease all those values by 10, and I should get the exact same looking figure. And I do. And it doesn't look like there's been anything wrong with it. It still looks like the same. Now I'm going to hopefully just increase this to a silly number right away and get that this would be 1 meg here. And then what's 1 meg is 1 microsecond. So edit my profile here to 10 micro, 5 micro, 5 micro, 0.1 micro. And you can see we've got some weird stuff coming out. The input, of course, is still the same, but look at the output. the output is not at all what the input should be. And that's because we've exceeded the frequency capacity of the circuit. We're trying to still just get a gain of 1, but we're exceeded the frequency. Now, we could just keep sitting here and playing with the frequency over and over and over again. But let's think about maybe what something we could do instead. So let's delete that and look at voltage AC. Connect that up. And then I'm going to delete, if my program doesn't go crazy on me, I'm going to delete these markers here. And what I'm going to do here is I'm going to do an AC sweep. And let's go ahead and start at 10 hertz. Let's go to 1 meg. And let's do 50 points per decade. And let's run that. Now, there's nothing plotted because we don't have anything here. So I'm going to go to markers, and I'm going to do advanced dB of magnitude. Now, I'm just going to go ahead and put one, maybe. Right there on the input. And of course, since it's 1 volt AC, it's going to be 0 dB because 1 volt corresponds to 0 dB. But now I'm going to do a dB on the output. And what can we see here? Well, it does some really crazy stuff off here, but what you want to look at is where do these start not lining up here? And you can see, like, well, wait a minute. They're starting to drop here. If I were to zoom in right here, that's not going to zoom me in, but if I were to zoom in right there, let's see here, zoom, fit, no, zoom, area. So if I were to zoom in right there, we can see that, wait a minute, even at 30 kilohertz, the output is not 0 dB, which it should be, because if I'm getting a gain of 1, it should be 0 dB, the output. So what that's telling me is my gain bandwidth product for this is actually much lower than 30 kilohertz. So what that's meaning is this design has actually got a terrible gain bandwidth product. And again, this is just a generic, simple design of an op-amp. Because even a 741, which is just a mediocre op-amp, has a gain bandwidth of 1 megahertz. And so we're not even in the hundreds of kilohertz range on this. But that's something else you could look into, is like, when you convert yours to an MPN design, what is your gain bandwidth product? All right, well, that kind of shows you all the things you can be doing with these simulations. There's other things you can do and maybe investigate, play around, but the idea is you want to design your circuit, simulate it, get as many interesting parameters that you can, simulate and compute as many of the parameters as you can, and then write up a nice lab report for it, or a nice report for it.